Hi, and welcome to session 9. We're going to talk about mechanical pressure in PhysiCell and contact testing to help a cell determine in its environment who is nearby for any kind of interactions. So the goals of this quick module here is to first define the mechanical pressure as implemented in PhysiCell, give an example of pressure-based phenotype function used for controlling proliferation, then talk about functions that are used for testing for contact with nearby cells, talk about a cell that's designed for ingestion so that one cell can actually eat another, very handy for things like predation or immune functions. And then lastly, show an example of a cell interaction rule, actually a contact rule in this, a custom rule in this case, that could use for predator-prey type codes. So let's just quickly talk about mechanical pressure. And generally speaking, pressure is defined to be force divided by surface area. It's like a force per surface area. So in the context of cell biology here, what we want is like a compressive mechanical pressure. That's the force imposed on your cell by your neighbor cells divided by your surface area. And so because in PhysiCell, our default mechanics use interaction potentials, we can use the repulsion potential to calculate these forces, or at least something that's proportional to the forces. You take the gradient of your potential functions for all your interacting neighbors. So if Ni is your set of interacting neighbors, sum this quantity up over all of your cells that are in interaction distance, and then divide it by your cell surface area, and you would have something that looks like pressure. Now in PhysiCell, remember that we don't track cell morphology. We track position and size, but not morphology, which means we really don't have a good approximation of cell surface area. So we want to normalize this out. So what we've done is we created a non-dimensionalized form of the pressure called simple pressure. It's stored in cell.state.simplepressure. And we've more or less come up with some normalization factors. So first, let's talk about a 2D tissue. If the 2D tissue, if you have a whole bunch of identical cells and they're in close packing, that would be a confluent tissue. No gaps between the cells, but no compression. And in that case, a cell would have 6 neighbors in close packing. It's like a hexagonal lattice. And so what you can do is you can say, take this interaction potential for 6 identical cells of identical size that are basically the equilibrium cell-cell interaction distance for close packing, and calculate this interaction potential, multiply it by 6, and that gives you more or less this quantity if you had 6 neighbors. And so you divide by that, and that would give you normalization. Likewise, in 3D, in a close packing would give you 12 identical neighbors. And so what we've done is we actually have normalized this for 3D. And so in 3D, your normalized, your simple pressure will be 1 if you have 12 identical neighbors that are in close packing with no compression. And that means that in 2D, you would only have half the number of neighbors, so your normalized pressure would be 1/2. So that gives you an idea of kind of the scaling of the simple pressure, and then you don't have to worry about surface areas or scaling or weird units. So let me give you an example of a phenotype that uses this kind of simple pressure. So here we have a pressure function, we'll call it pressure phenotype. It has a standard form of a cell pointer, phenotype passed by reference, and a small amount of delta t to advance your model, this function here. So first we do the standard trick. We're saying for my cell, I'm going to get the cell definition. That's kind of like my parent type here. So remember the cell, we're within the cell now, but we can do a find cell definition for my cell's type, and I'm going to store it as a static cell definition pointer. The static means that basically the first time you enter this function, you're going to evaluate this and store it into this variable that is stored basically stored within this function. So every time you enter this function, this is available, and that means that you only have to do the search 1 time. You don't have to do it every time you enter this function. The other little trick we're using, right, is that if the cell is dead, we might as well not bother continuing. So we're going to exit the function, and more than that, we're going to overwrite the update phenotype pointer with the null pointer, so that we never enter this function again once we know the cell is dead. Now, supposing the cell's alive, I'm going to compare my pressure, my cell state simple pressure, to some kind of a pressure threshold that is stored in a custom variable in my cell. And if I'm below my threshold, I'm going to allow the cell to cycle. And so what we'll do is we'll take my transition rate from phase G0, G1, basically, to phase S. I'm going to take that transition rate and grab it from my parent line, from my cell definition. So cell definitions phenotype that rate. And I'm going to set a custom variable of arrested to 0. But if my pressure does exceed the threshold, then I'm going to overwrite that transition rate from phase 0 to phase 1 to 0, and I'm going to put the cell in an arrested state and then exit the function. So let's give you an example of this thing in use. I've selected the separated flow cytometry model where we have G0, G1 phase, S phase, G2 phase, and M phase. So 4 phases altogether, indexed from 0 to 3. And I sped up the transition rates just so we can kind of get a really fast example here. And for color coding, all the cells are just kind of sprinkled randomly in the domain. They are in a non-arrested state, but they're not cycling. So we'll build those as cyan. And cells that are not been arrested want to enter the cycle stochastically, so they want to go from cyan to orange and trying to fill the space. Now, as the cells fill the space, eventually going to press on each other, and they're going to exert a pressure on one another, and they ought to go into pressure rest. But remember that also this tissue has apoptosis events. So there will be random cell death events. You see that pop it as black cells. And when those apoptotic cells shrink, they relieve the pressure on the neighbors, right? Because now they have more like 5 neighbors instead of 6. And that ought to allow them to exit the arrested state and go back to non-arrested state and then go back into cycling. So let's see what this does. Let's just click on the movie here. So we see this proliferating, and you get these flashes, between, more or less most of the tissues in arrested state because there's a high pressure. But look around these black apoptotic cells, and you see that around a lot of them, that has freed up some space and it has reduced the pressure. So the cells nearby these apoptotic spots are, either cyan or orange, where they have been allowed to enter the cycle and start filling up the space. So that's actually kind of cool. Now, on the other hand, you could even do other functions like this. You could say that if my pressure goes way too high, maybe that's a stress on the cell, and you might want to have pressure-induced apoptosis at a very high level of pressure. So that's something you could do to kind of counterbalance this. Notice here that in these empty spaces near the apoptotic cells, a whole bunch of cells have decided to enter the cycle basically at the same time. So this thing may kind of go up and down, above and below some kind of a target threshold, because we need probably some more active control. So that leads me into another sample where maybe you want to add an additional chemical signal. Say that cycling cells may secrete a chemical signal, a diffusible signal S, that diffuses into the domain and suppresses cycling by nearby cells. So here's kind of the behavior I would expect here, that apoptosis events, let's say you have a confluent tissue, an apoptosis event would temporarily relieve the pressure on the 6 neighbors. All 6 of those neighbors want to proliferate to fill that gap, but this is a stochastic model, which means that one of them stochastically is going to enter that cycle first, and that cell will secrete this chemical signal that diffuses out into the domain and tells the other 5 cells, don't bother, I'm on the job, don't proliferate, and then they'll go back into an arrested state. So let's see what happens if we build this kind of a rule. So here I'm going to query my microenvironment to say, where is my diffusing signal? And I'm going to store that index statically as end signal. And then I'm going to basically sample this, right? That if I'm cycling, if I'm actively cycling, which means I'm not in phase 0, then I'm going to turn on my secretion rate of this signal, which is kind of a low level of secretion rate here. Otherwise, if I'm not cycling, I'm going to turn my secretion of this chemical factor off. And now I'm going to start comparing, I'm going to start looking at the signals in my environment. Say that, I'm going to go and query the environment. So go to my cell nearest density vector, evaluating, okay, so that's a vector of all the substrates in my environment, look at the signal index to get the signal out of it, and I'm going to compare it to a threshold. And if I'm below a threshold, I am not signal arrested. And if I'm above the threshold, then I am signal arrested. So just set these 0 or 1s. And then likewise, I'm going to compare my pressure to the threshold. Say that if my simple pressure is below the threshold, then pressure rested is 0, otherwise pressure rested is 1. And I'm going to use these 2 variables together to decide what to do. Now remember, custom variables in a cell are doubles, they're not integers. So you can't compare directly with the equal sign to 0 or 1. It's better to just say that if it's greater than 1/2, then it's 1. So if it's either pressure arrested or signal arrested, then I'm going to go ahead and set my transition rate to 0. And otherwise, I'm going to set my translation, so here, if I am arrested by either condition, transition rate is 0. Otherwise, I will allow the transition to continue. And so the transition rate is going to be grabbed from the parent cell line. And actually, I see a slight bug here. I didn't use the right parameter name. It should be signal threshold here and signal threshold over here. Actually, no, sorry. It should be signal arrested over here. So this should have been signal arrested, not signal stop. So this is a slight bug actually in this example. So let's look at the result here. So Here I'm going to add a few more colors for the different states, right? That if it's pressure arrested only, be blue like before. But now, if it's signal arrested, it'll be kind of this crimson red. And if it's both signal arrested and pressure arrested, it'll kind of blend these two colors and make it a purple. Otherwise, everything else is the same. So let's go ahead and watch this video here. So let's pause. Oops, let's go back and play this. I want to pause it and kind of show what's going on here. We have a whole lot of confluent tissue where they're pressure arrested. And now here in some of these open gaps, we have a few cycling cells before they are sending out the signal, which is suppressing proliferation. So look at this red cell here. This one has been suppressed cycle entry because of the diffusing signal. And then these purple ones here have both high pressure and the signals. They're also pressure arrested. So this is kind of reducing the number of cells that respond to the apoptosis events to fill the gaps. And you can kind of see how these waves propagate through the tissue. But this little bit more complex regulation, I think, gets you a little bit closer to homeostasis in the tissue. So you see here we have, a lot less proliferation than we had earlier because we have kind of this dual control. Now let's kind of switch topics to testing for contact. As of very recent versions of PhysiCell, the interaction potential functions that in the default mechanics will actively update this variable here called neighbors. It's a vector of cell memory addresses or cell pointers. So you look in PCell in cell.state.neighbors, that's a vector of cell pointers that were found to have non-zero adhesion or repulsion interactions in the potential function. It's updated every single mechanics time step. So as long as you haven't changed your out of your default mechanics model, this thing will be actively updated for you. So this gives you a really nice way to test for interactions. There are a few backup functions as well. You can actually basically, you can go up to the underlying mechanics data structure called, it's like a container. And we've created a quick interface function that will give you a vector of memory addresses. Basically by reference, it will go and grab that memory address, that data structure, say, in my little mechanical voxel, who is interacting with me? Now I want to point out that, this is really, really fast, which is great, but there are a couple of problems. First of all, if a cell's near the edge of mechanics voxel, it could be interacting with cells in the next interaction voxel, but we're not querying for that. So you're going to miss some interactions, but wow, it's dirt cheap. The other thing is the cell itself is in that container, which means that it is in this list. And so if you're going to do some operations on it, you first want to make sure that you're not like trying to interact with yourself. So be really careful when you use this function, but it's way fast and cheap. Another possibility is we basically expanded this to make a function called nearby cells that will check not only my mechanics voxel, but the ones nearby and concatenate them into a bigger vector of memory addresses. So that's a more complete list, but it comes with a little bit of extra computational cost of creating and concatenating that list, all the memory copy operations, things like that. And also this will include your own cell because it includes, it's in one of those containers. The last thing you can do is basically, supposing that you're not using interaction potential functions, you may want to basically use the exact same calculations to calculate who is nearby. And so we could basically create the exact same data structure or the exact same list that we would have gotten without the interaction potentials. But there, as of recent versions of PhysiCell, you probably will never need to use these three functions. Also, they're just some like global versions of it where you pass the cell as the input argument rather than as member functions. So these are possible as well. Ingestion is one more function we should talk about here, where a cell, say, let's call it a predator, can eat another cell. Let's just call it the prey for simplicity, or attacker and target or something like that. And what it'll do is the prey cell's volume will be added to the cytoplasmic solid volume of the predator cell. The fluid volume of the prey cell will be absorbed and put into the fluid volume of the predator cell. The prey's cell volume will all be set to 0. Just zero the thing out. Inactivate it by setting all the functions to null. Set secretion uptake rates to 0, and detach any cells that you've attached manually. That's be the topic of section 10. And likewise, the predator's volume, then, it still has a volume regulation model, and it is now over its target volume, so it's going to try to shrink back towards its normal volume. So this could be useful for predation, such as by, like, say, macrophages. And the syntax of the function is my cell will say, ingest cell and then pass your target cell's memory address into it. So let me show you an example of a very simple custom cell rule that you might want to put in the mechanics time step. It's called custom predator function, same classic form, cell pointer, phenotype of reference, and DT. And we're going to do our now standard trick of looking for the cell definition of not my type this time, but for prey. So somewhere in the simulation, there's something called prey cells. I want to go search for them. And then I'm just going to iterate over my list of neighbors. So for every cell in my list of neighbors here, so using that state variable we talked about earlier, I'm going to go and grab its memory address and just give it a quick shorthand of PC. And if that cell that I am checking against is a prey cell, then I'm going to eat it. And that's it. That's the function. And just here's an animated GIF of that in motion, where we have red cells here chasing gray prey cells. And they won, right? So the gray cells are dividing, but the red cells are chasing them down and eating them. And notice how they get bigger, right, whenever they eat something, because they've absorbed that volume. Right, so watch some of these, they're chasing the cells to get bigger and then to kind of start shrinking back down again. So you can see the well-fed cells here are kind of a bright, big red circle. And that's it. So thank you very much for tuning in. And the next session will be session 10.